And what we'll see in this video is that the solution to a differential equation isn't a value or a set of values. Rather, it's a function or a set of multiple functions. So when we think back to what we know as particular solutions, this was when you did the integral of a specific function and then you would get an output of plus c. That's not a particular solution because you still have a constant, an unknown constant. But a particular solution is when you have that constant value equal to some value. Once you find that value, that's your particular solution. And then you can plug that back into an equation, and that will give you the original equation. And then that original equation would be the solution to a differential equation. So let's take a look at an example. So if we're given dy over dx is equal to to the power of 2x minus 2x squared, and we're told to find the particular solution of y if we're given that y of 0 is equal to 4. So we have an initial condition, but we don't have our particular solution. However, we can find it by taking the integral of this. So when we take the integral, this gets rid of the derivative and just will leave us with y. So then y will be equal to e 2x. And what I'm actually going to do is I'm going to separate these two values. So this would be dx minus the integral of 2x squared dx. Now with this first integral, we can just use u sub where we can set u is equal to 2x and then do the derivative to both sides. Du is equal to 2 dx. And then we can isolate dx by dividing both sides by 2. So then we're left with du over 2 is equal to dx. So then divide both sides by 2. We're left with du over 2 is equal to dx. So then we can substitute that back into here. So we're left with the integral of eu over du over 2. And this is a straightforward integral, which is going to be 1/2 times eu. But because eu was 2x, we can just do 2x. And then we'll do this integral now, which we can just simply take out this 2, which will leave us with negative 2, the integral of x squared dx. And this should just be a straightforward integral where we just apply anti-power rule. We're left with negative 2 x cubed over 3. And then we can put that here over 3 y. However, we're forgetting one thing, and it's one of the most important things, and it's why we're actually verifying, is plus c. Now, again, we do have a plus c, but we don't have a particular solution. So the way we find that is by plugging in our initial condition, right? So we're given this initial condition, and then we would solve for c. So we know that y is equal to 4, so we can, so here, I'll actually move this up here. And we're left with 4 is equal to 1/2 e, and then we know that anything times 0 is going to be 0, so that's just 0, minus, again, 2 times 0 cubed. 0 cubed is just 0, so 2 times 0 is just 0. So negative 0 over 3 is just going to be 0, so this whole thing just comes out to be 0, plus c. And we know that anything to the power of 0 is just going to be 1, so we're left with 4 is equal to, I'm going to write this as a decimal form so it's easier to subtract. 4 is equal to 0.5 plus c. And we can see that when we isolate c, so we'll subtract 0.5 from both sides, we're left with c is going to be equal to 3.5. Now, this is our particular solution, but we should plug it back in. So we should be left with y is equal to 1/2 e 2x minus 2x cubed over 3 plus 3.5. Now, you can always verify your solution because you know that this is the integral of your derivative. So to verify, you can just simply do the derivative of this function, and then you should get this. And if you don't, then that means that something must have gone wrong, and then you should probably check your antiderivatives, or if you did use sub, your derivatives. Now, in the context of like an AP exam, such as AP Calculus, you'll often won't get such a direct problem where it's telling you you're given this derivative and this is your initial condition, find the particular solution. Oftentimes you'll hear something along the lines like this. A curve has a slope of e to the power of 2x minus 2x squared at each point on the curve. what is the equation for this curve if it passes through the point 0, 4? So one thing that you can always do whenever you have a word problem like this is that when you hear curve, just think back to the function. So the problem would read, you if you have a function with the slope of e to the power 2x minus 2x squared at a specific point, right? So you know that on this function, at a specific point on that function, you have this slope. It creates this slope. And you're told to find an equation for the function if it passes through the curve that you know the slope is such as this. It sounds kind of weird, but you get used to it as you practice more. But it's important to understand that when you're verifying solutions, it's not just a value or a set of values, but rather a function or a set of functions. We can take a look at another example that's a bit um, more complicated. So this will be the last example because so what I do hope you take away from this video is that you understand that when you're verifying a solution for differential equations, is you have to understand that the original equation, so the f of x equation, just the original equation, will be the solution to f prime or f double prime or f to any higher degree. It's that original is going to be the solution to those, right? So when you understand what it means to verify or find a solution to a differential equation, you should always think back, okay, do I have an initial condition? And then if you do, okay, then you can plug the initial condition to find your particular solution. So when you apply the logic in this specific example, right, we understand that we're given a 2-degree derivative, or uh, d squared y over dx squared is equal to 1 over x squared plus 1 minus 2x all squared. And then you're given the initial condition of y prime of 1 is equal to 7 over 6, and y of 1 is equal to 0. So because we have an initial condition and we're told to find the particular solution of y, then we can just find the integral of this function 2 times, because we have a second degree derivative. Then we can just do the antiderivative 2 times, and then we should get back to the function of y while plugging these initial conditions to solve for the constant c. So if we know that dy over dx is going to be equal to the integral of this, and actually I will separate this out into 2 separate integrals. So we'll have, and then another thing that I'm going to do is I'm not going to have an x value in the denominator, but rather I'm going to write it as a negative exponent. So we'll have x negative squared plus the integral of 1 minus 2x squared, and I forgot the dx, so dx. Okay, cool. So for the integral on the left side, this is a simple derivative that you should be able to do. So it should be x negative 1 over negative 1. And in here, we will actually apply u sub. So we know that u will be equal to this. So we can just say u is equal to 1 minus 2x. Do the derivative, we're left with du is equal to negative 2 dx. And we know that du is equal to du over 1, 2 is equal to dx. So then we understand that this will just be u squared times, or u squared, and then we can do the antiderivative of that, which would, so then we're left with the integral of u squared, and then dx we substitute for du over negative 2. And then we can just write this as 1/2. And then the antiderivative of x squared, or a variable squared, is going to be u cubed over 3. And we know that that u is 1 minus 2x. So 1 minus 2x cubed over 6. And then we'll add that to this. 2x over 6. And then we cannot forget the constant, so we will add the constant. And we know this is all equal to du over dx. However, the du over dx is still a derivative. It's not the original function. So therefore, we have to be able to do the antiderivative again. However, we cannot do the antiderivative yet because we still have a constant and we haven't found the particular solution to this first derivative. So we have to plug in our values, and we know that d prime of 1 is equal to 7 over 6. So we know that this should be set to 7 over 6 is equal to 1, but then 1 to the negative power will just be negative 1. Okay, and then we plug in 1 in here. We would get 1 minus 2, which would be negative 1. Negative 1 cubed is just negative 1. So we're left with negative 1 over 6 times negative 1, which would just be positive 1 over 6. And in this one, since all numbers have a common denominator of 6, we can just rewrite this as 6 over 6 and plus c. So this makes it easier to simplify. So then we know that this when you combine like terms, it would be negative 5 over 6. So what we can do is add negative 5 over 6 to both sides, which would just give us c is equal to 12 over 6. And that can just simplify to 2. And here I'll move the board a bit down. All right. Okay, cool. So therefore, now that we know this, we know that the particular solution to dy over dx is just going to be dy over dx is equal to negative 1 over x minus 1 over 6 of 1 minus 2x cubed. This was originally plus c, but because we know that c is equal to 2, we just do plus c, or plus 2, right? Now we're one step closer to finding the particular solution of y, right? If it's asking us to find the particular solution of y prime, then this we could stop here and this would be our answer. However, we're not asked to find the particular solution of y prime, but just y. So we have to find the integral of this value again. So we know that when we antiderive dy over dx, we're left with y. So y is equal to the integral of negative 1 over x dx minus 1 over 6. Remember, I'm just taking this out of the integral because it's multiplication. The integral of 1 minus 2x cubed dx. And this is going to be plus the integral of 2 dx. So we know that the antiderivative of 1 over x is just the natural log. So and because we have a negative, we can just take that out. So we know that y is equal to the negative natural log of x. And for this, we just use u sub. But we know we can take this 1 over 6 out. 1 over 6. Here, let me write this negative a bit more clearly. Negative. So we to make it easier, I'll write it down. Right here should be enough space. So we know that u is going to be equal to 1 minus 2x. The derivative of both sides is du is equal to negative 2 dx. So then dx is simply equal to du over negative 2. So then we can substitute this in into here, which here, right, since I do not have a lot of space, I'm going to write it up here. Du cubed over du negative 2. And we know that this will just be u to the fourth power over 4 times negative 2. So this should be negative 8. And then because we have that 1, 6, it would be 8 times 6, so 1 over 6. And we know that 8 times 6 is just simply 48. So we're left with u to the fourth power is equal to 48. And you can't forget the negative. And then we go back to what u was originally, and we know that u is equal to this. So we should erase this. And we're left with negative u is 1 over 2x to the power of 4 all over 48. And we know that now we do this derivative, which would simply just be plus 2x. Now this is a lot of work, but this is what you will have. I mean, you won't always get examples or problems like this, but this one is just particularly difficult just to show you the actual process that you need to go through to find the particular solution of y when you're given a second degree derivative. So now that we have this solution, right, we still forgot our plus c. Now we're almost there. Now we just need to plug in our initial condition, which our initial condition, we're told that y of 1 is equal to 0. So we just plug in 0 is equal to negative natural log of 1. And we know that the natural log of 1 will just be 0, so this just goes to 0. And then negative the 1, well, that simply will just be 1 minus 2, which would be negative 1. Negative 1, uh, or it would be negative 1 to the fourth power, which would be positive 1. So then we're left with plus 1 over 48. Sorry about that, the video cut off. But where we left off was that we were at 1 over 48, and we were plugging in the initial condition of y of 1 is equal to 0. So after we plug it in, we would also get 96 over 48 plus c. And because we know this is set equal to 0, we can simply subtract these. And because they have common denominators, we can also just add them. So we're left with 97 over 48 plus c. And we can isolate c by subtracting 97 over 48 to one side. And we're left with c is equal to negative 97 over 48. Now that we have our constant, we can create our actual particular solution to our differential equation. So now that we have all of that, we can go back to our original equation, which was y is equal to negative natural log of x plus 1 over 48 times 1 minus 2x to the power of 4 plus 2x. Now, we originally, before we solved for the constant, we said plus c. But because we solved for the constant, we can now plug in the constant we solved for, which was negative 97 over 48. And now this is our actual particular solution of y. So what I hope you take away from this video is that you now have a better understanding of how to verify or find the solution to differential equations, which is to have the original function or the original set of functions. And you can always verify these functions or function by taking a derivative of that. And if the derivative of the original function gives you the given derivative from the problem, then you know your answer is correct. Now, as always, I recommend to do more practice because now that you have this understanding, now it's just a matter of fact of getting good at doing derivatives and getting good at doing antiderivatives.